Log on, tune in, find out. Another good idea from Cambridge.
It's a pleasure for me to welcome Yuqin Yao from Tsinghua University, and she's going to speak on a new extended discrete KP hierarchy and generalized pressing method. You can see the top. Thank you.
Good afternoon, everyone. I first appreciate the organizers to give me this opportunity to report our work. This work is a joint with Dr. Liu and Professor Yunbo Zheng. What I will talk includes these 5 sections. Generalizations of the Soliton hierarchy attract a lot of interest from both physical and mathematical points. For example, the multi-component generalizations of KP hierarchy have been researched by many scholars. The discrete KP hierarchy is also an important object in the research of the discrete integrable systems and the discretization of the integrable systems. Our work is to construct the extension of the discrete KP hierarchy and prove that the extended discrete KP hierarchy is integrable and solve it. In this section, we construct the extended discrete KP hierarchy. In our work, we denote the shift and the difference operator gamma and delta respectively as follows. This is the shift operator and this is the difference operator. As for the difference operator, we can also define its adjoint operator by delta star. We know this equation is the Lax equation of discrete KP hierarchy, where L is such a procedural difference operator. Bn equals Ln plus stand for the difference part of Ln. From this equation, the commutativity of the Tn flow and the Tm flow gives rise to the zero curvature equation for the discrete KP hierarchy, and its length pair be given by the formula 6. In this zero curvature equation, if we take n equals 2 and m equals 1, we can get this discrete KP equation. It is known that the squared eigenfunction symmetry constraint can be given by these 2 equations, which is compatible with the discrete KP hierarchy. Based on this constraint, we can construct this hierarchy 8. Compare this hierarchy with the discrete KP hierarchy, we can find in this hierarchy a new Tolkien law has been introduced, and more component psi I and phi I has been added in this hierarchy. What's more, in this hierarchy, if we delete this part and change the Tolkien flow to the Tm flow, this hierarchy becomes the discrete KP hierarchy. In this sense, we can say this hierarchy is the extension of the discrete KP hierarchy, so we call it extended discrete KP hierarchy. For this hierarchy, we can also give its zero curvature equation and the length pair. We first give a lemma. Let Q is such a difference operator, then these 2 equations hold. And this lemma, we have this proposition 1. This proposition means and this equation 8.3 the commutativity of the first two equations gives rise to the zero curvature equation for the extended discrete KP hierarchy, and its Lax representation can be given by the formula 11. Here we have a remark. From the extended discrete KP hierarchy, we can see it contains two time series Tn and tau k, and more components by adding the eigenfunction psi I and the adjoint eigenfunction phi I. From the extended discrete KP hierarchy, we also can obtain two types of equation with source. For example, if we take n equals 1 and k equals 2, we can get the first type of discrete KP equation with source. We look at this equation. In this equation, this part is just the discrete KP equation, and this summa is called the source. Its element psi I and phi I satisfy these two equations respectively. And for this equation, its Lax representation can be given by the formula 13. If we take n equals 2 and k equals 1, we can get the second type of discrete KP equation with source. That is this equation. In this equation, the summa is the source, and its element satisfies these two equations respectively. For this equation, we can also give its Lax representation. That is this formula. The extended discrete KP hierarchy enables us to find the first and the second type of discrete KP equation with source and their Lax representation in a different way from the existed method. For the extended discrete KP hierarchy, we can get its two reductions. The first one is the Tn reduction. The Tn reduction is given by this equation, and this condition we can drop Tn dependency from the zero curvature equation and obtain this hierarchy. This hierarchy can be regarded as the one-dimensional discrete integrable system with source, and its Lax pair can be given by these two equations. In this hierarchy, if we take n equals 2 and k equals 1, we can get this equation. This is a one-dimensional equation with source. Here, the summa is the source. This equation can be transformed to the first type of Wesloff-Chabit equation with source. The second is the tau k reduction. The tau k reduction is given by this equation. Under this condition, we can drop tau k from the zero curvature equation and obtain this hierarchy. This is the k-constrained discrete KP hierarchy. In this hierarchy, if we take n equals 1 and k equals 2, it from this equation hierarchy leads to this equation, which can be transformed to the second type of Wesloff-Chabit equation with source. Remark 3. The reduction leads to the k-constrained discrete KP hierarchy, including the first and the second type of one-dimensional solution equation with source. So the extended discrete KP hierarchy provides a more general approach to find two types of one-dimensional and two-dimensional solution equation with source, and their next pair can be given. We know the dressing method is an important tool for solving many solution hierarchies. For example, it can be used to solve the KP hierarchy, the discrete KP hierarchy, and so on. But this method cannot be directly applied to the extended discrete KP hierarchy. So in order to solve the extended discrete KP hierarchy, we should generalize the dressing method. Here we first briefly recall the dressing method for the discrete KP hierarchy. Assume that the operator L can be written in the dressing form. If W satisfies this equation, then L satisfies the next equation of the discrete KP hierarchy. Proposition 2. Assume that HI satisfies this equation and W is the ratio of such two determinants. Here the denominator is this determinant. Then W and L satisfies the equation that W10 satisfies. That is this equation. And the next equation of the discrete KP hierarchy respectively. This is the dressing method for the discrete KP hierarchy. We now generalize the dressing method. First, we give a lemma. Lemma 2. If W satisfies the equation that W10 satisfies and this equation, then L satisfies the extended discrete KP hierarchy. The dressing operator W is constructed as follows. We let Gi and Gi bar satisfy these two equations respectively, and Hi is the combination of Gi and Gi bar. Psi I and phi I is defined by this expression. So we have the proposition 3. Let W be defined by 24 and 27. L is such a dressing form. Psi I and phi I be given by this equation. Then WL, psi I, and phi I satisfy the equation that W10 and W tau k satisfy, and the extended discrete KP hierarchy. This proposition is very important in our work. To prove it, we need the following lemmas. Lemma 3 means the inverse of W equals this sum. Lemma 4 means W star acts on the adjoint eigenfunction phi I equals 0. Lemma 5 means this operator is a non-negative difference operator, and it acts on Hj equals delta Ij. And these three lemmas, we can prove the proposition 3. Here we give the key step in the proof. Taking partial tau k to this identity, we can find this operator act on Hi equals 0. Because This operator is a non-negative difference operator, and its degree is less than n. So it cannot annihilate n-independent functions unless this operator is self-vanished. So thus we prove the equation that W Tokay satisfies. This is the generalized dressing method for the extended discrete KP hierarchy. Having the generalized dressing method, we can get the uncertain solutions for the extended discrete KP hierarchy. For the first type of discrete KP equation with source, we take the solutions of 26 as follows, and HI is their combination. Because the pseudo difference operator L can be written in this dressing form. In this dressing form, if we expand the operator W and the inverse W, then compare the coefficient of F0 on both sides, we can get the expression of F0. Then F0 psi I and phi I can give rise to the uncertain solution for the first type of discrete KP equation with source. When n equals 1, we can get the one-solitary solution. If n equals 2, we can get these two solitary solutions. As for the second type of discrete KP equation with source, we can take the solution of the equation 26 as follows, and HI is their combination. Similarly, we can get the expressions of F0 and F1. Then these two functions together with psi I and phi I can present the uncertain solution for the second type of discrete KP equation with source. That's all. Thank you.
Any questions? Everyone's really very warm this afternoon.
Delta minus 1, which delta is a difference operator, which has a kernel. And you have delta minus 1. How you understand is it everything consistent how you work with the kernel? Delta minus 1 is not defined in the whole space of sequences.
Sorry.
Delta is a difference operator, right?
Yeah.
So it's not invertible operator. It has a kernel. If you act by delta on a sequence 1, 1, 1, 1, you receive 0. So
Yeah.
that is in a kernel. And you freely use delta minus 1 and all these sequences. Is it? Did you take any care about these sequences? Any conditions?
Which one equation?
A couple of slides ago you had, 2 slides before you had delta minus 1. In your, oh no, just no.
This equation?
Maybe you can discuss.
Okay, we can.
Could I ask a question? You have the solutions to your extended case. Do they differ from in what way do they differ from the standard discrete KP solutions?
You mean the extended equation?
The extended one, yes.
It's, I think it's different from the existed extension equation.
Okay. So maybe we can discuss it. It was just I missed exactly what the solutions were discussing.
Okay.
If there's no more questions, maybe we could thank the speaker again.